Hello everyone, let's take a look at LeetCode 1804, implement try 2. It's a follow-up of implement try 1. So if you haven't practiced implement try 1, you can practice that problem first since they are pretty similar. Okay, so let's take a look at the problem. A trie or perfect tree is a tree data structure used to efficiently store and retrieve keys in a data set of strings. There are various applications of this data structure, such as autocomplete and spell checker. So we need to implement 5 functions. The first one is constructor. The second one is insert function. We need to insert a word into the trie. Note that we can insert a same word multiple times. The third function is count words equal to, so we need to return how many times of this word in this trie. For example, we insert apple 3 times, then this function will return 3. Okay, the first function is count words starting with a prefix. Okay, the last API is erase function. Note, the problem mentions it's guaranteed that for any function called to erase, the string word will exist in the trie. Okay, let's take a look at example. We insert apple twice, then we count apple. We will get 2. For starting with app, we will also get 2. Erase apple. Now we still have 1 apple in this trie, so this function will return 1. We erase apple again, then this function will return 0. Okay, let's take a look how to solve this problem. First, let's recall what trie is. So first try we start with a root node. Then for each word we want to insert, we will new some node. If the node does not exist, we will new a node. Otherwise, we will reuse the existing node. And for the last node, it's a word, so I will just mark it green to be noticeable. Then we insert apple. We will reuse those nodes. Then we insert some new node here. Okay, for this is basic trie node struct. We have a trie node star array. Since the letter is only in lowercase, so the size is 26, and we initialize them to non-pointer here. And I also have a trie node star root, and in my constructor, I will new it. Okay, let's implement the first function insert. For this function, it's pretty simple. We just for loop each character in this word. And for each node, we try to find if it has a corresponding child. If it does not exist, we just new trie node. Otherwise, we can just use the existing node. Okay. Next, let's implement count words equal to. For example, we insert app, we insert apple. For apple, we will just return 1. Okay, so the code is very similar. We just iterate each character in this word. And for example, if a node does not exist, we will just return 0. For example, if we query hi, in the root node, the h node point to a non-pointer, so we will just return 0. Otherwise, we will just go to the correct child node. At last, we will return something. For example, if we query apple, at last, the temp node point to this green node. And how can we get the count information? So for each node, we should have a variable called word count, and we initialize to 0. And where do we update it? So when we insert a word, at last, we should increment the word count. So at this point, we can just return the word count. If we insert app first, the word count of this node will be 1. Then we insert apple twice, the word count of this node will be 2. Okay, so that's all good. Let's implement the next function. The next function is count words starting with. So we have a prefix. The code is almost exactly the same as the previous function. So we're just trying to go to the correct child node. And what should we return? For example, for app, we know we should return 3 since we have 1 app and 2 apples. They all start with app prefix. So we should have another variable similar to word count. We should have prefix count, and we also initialize prefix count to 0. Like when do we update it? In insert function, as long as it goes through this node, we should increment it once. So we will update it here. Increment the prefix count. Then in count word starting with function, we just return the prefix count. If we insert app once and insert apple twice, the word prefix count will look like this: 33322. Since only apple goes through those last two nodes, so the prefix count of them is 2. Okay, so far so good. Let's implement the last function, erase. The basic framework is very similar to the previous function. We just try to find the last node. Okay, as the problem mentions, the word is always a valid word. It do exist, so we don't need to track non-pointer. So if we erase apple, finally the temp node will point to this green node. Then we just decrease the word count, like from 2 to 1. So next we query apple, we will get word count 1. But there are problems since we haven't updated prefix count. If we query like how many words in my try start with prefix app, we will return 3 here. We will go to app, then we stop at this node. We will return 3, which is incorrect since we erased one apple, so we should return 2. So in erase function, we should also update prefix count. So for each node, we go through, we should decrease the prefix count like this. Now, if we query how many words start with prefix app, it will return 2. Assuming we erase one more apple, so it looks like this. For the last two nodes, the prefix count becomes 0 since we have 2 apples and we now erased all of the 2 apples. Okay, so far so good. The code can pass the test, but there are some remaining problems. One of the biggest problems is like we are wasting a lot of memory. We know we may use this try to do a lot of operations. We insert maybe thousands of times, we erase thousands of times. So there will be a lot of nodes, like with prefix count 0. We know it's for this node, they're useless since the prefix count is 0. They does not contain any useful data. So we should delete them from memory to free our memory. Otherwise, they use up a lot of memory. Okay, and we should also disconnect this pointer. Since if we have this pointer, which means like we have word, for this node, there's a try node that start with L. But the prefix count is 0. This pointer should point to a non-pointer, right? So there are two things we should do. We should reset it to a non-pointer, which means it does not have this child. The index is L. And we should also delete or free those memories. Okay. Let's see how can we achieve our goal. Assuming my temp node is pointing to this node, and we just decrease prefix count from 1 to 0. Okay, then I realized the prefix count is 0, so we will do additional stuff here. And at first, we have to be deleted pointer. It's initialized to non-pointer. And we will stop a parent node first. So my temp is here, my parents is here. Then I realized to be deleted is non-pointer. So we will update this pointer to a non-pointer, right? So node's index is pointer to a non-pointer now. So we correctly updated this pointer. Okay, next I set to be deleted to be temp. So to be deleted point to this node. Okay, now we continue our for loop. Temp is pointing to the child node here, and we decrease prefix count. So prefix count becomes 0. Okay, now temp is here. We can happily or we can safely delete the to be deleted node. So we found to be deleted is not non-pointer, so we can just delete it. Okay, sounds good. So far, so good. Okay, now prefix count is still 0, so we set to be deleted to be temp. So to be deleted point to this node now. Okay, at last, we finish our for loop. We just decrease word count from 1 to 0. At last, I still need to track, since for my last node, for this leaf node, it still hasn't been deleted, so I will do the last track. If to be deleted is not non-pointer, I should delete it. Okay, so now we clean up our memory. That's a final solution. Okay, thanks for watching. See you next time.